Every biological rhythm we have, every societal structure we've built, is tuned to exactly one frequency, 24 hours. Because the sphere takes that long to complete a single rotation, we naturally assume this pace is the universal standard for how time works. Looking at our neighbors seems to confirm that assumption. A day on Mars lasts 24.6 hours. It's a rhythm so familiar that human clocks would only need a minor adjustment to tick to a nearly identical rhythm. But that baseline disappears the further out we look. Jupiter is the most massive planet in our solar system, yet it completes a full rotation in just 9.9 hours. Looking inward, the disparity increases. A single day under the thick haze of Venus takes 5,832 Earth hours. Even more unusual, it spins backward compared to almost everything else in the neighborhood. Every planet here formed from the same ancient disk of swirling stardust. All of these wildly differing planetary clocks are the result of specific, powerful forces that shaped the early solar system. The outer solar system is dominated by speedsters. It's a strange paradox. The largest planets in the system, Jupiter, Saturn, and Neptune, possess the absolute shortest days. This occurs because of the principle called the conservation of angular momentum. When these planets were young, they existed as wide, scattered clouds of gas and dust. As gravity caused those clouds to collapse inward toward a dense center, the spin rate began to exponentially accelerate. This is the same physics that causes a figure skater to spin faster the moment they pull their arms in close to their body. The blurred horizontal storms on Jupiter result from this rotational energy. The planet spins so fast that the atmosphere is stretched into distinct high-speed bands. A frantic, sub-16-hour day on a gas giant is the physical record of the massive gravitational vacuum created during that planet's birth. Near the center of the solar system, the pace changes. On Mercury, the rotation is so sluggish that a single day takes over 1,400 Earth hours. The Sun is responsible for this lethargy. Its immense gravity exerts a constant influence on any world orbiting this close. This is gravitational drag. The Sun's pull is so powerful that it can actually warp the shape of a planet, creating a physical bulge that the Sun's gravity can latch onto. As the planet tries to spin, the Sun's gravity pulls back on that bulge. Over billions of years, this friction bleeds away the planet's rotational energy, acting as a massive gravitational brake. A slow day near the center of the solar system shows that a planet's spin is dictated by its proximity to the overwhelming power of its host star. Venus remains the ultimate anomaly. Its day lasts over 5,000 hours, and it rotates in the opposite direction of every other planet. Neither gravitational drag nor the conservation of momentum can explain why a world would completely reverse its natural spin. This suggests a planet-shattering kinetic impact. Early in the solar system's history, a massive celestial body likely collided with Venus off-center. A collision of that magnitude carried enough force to knock the planet off its original axis and physically overcome its forward momentum. The backward rotation of Venus is a planet-sized scar, left over from a time when the early solar system was a violently destructive environment. When we look at all these worlds together, we see a solar system ticking to many different speeds at once. The specific duration of a planet's day reveals the physical events it has survived since the solar system first formed. Fast, blurring rotations are the signature of preserved momentum. Sluggish crawls are the result of gravitational drag, and reversed spins point to the impact of ancient, massive collisions. Measuring the length of the day on another world provides a direct look at the chaotic forces that built our corner of the galaxy.